In this video, I will show you how to use the second derivative to find the intervals on which a function is concave up or concave down. I will also show you how to find the points of inflection where the function changes concavity. Let's rewrite number 7 a little bit before we try to take the derivative. So let's bring this denominator up. So we can write this as 24 times x squared plus 12 to the negative 1 power. So now we can find the first derivative using the power rule. Well, the chain rule, really. So we will do negative 1 times 24 and get the negative 24 as we take the derivative of the outer function. We decrease this by 1, so that's negative 2. But then we have this inner function. So we'll just write this down, x squared plus 12. But the chain rule demands that we multiply by the derivative of this inner function now. So that'll be 2x. Let's go ahead and clean this up a tiny bit before we find the second derivative. So we can say, well, 2 times negative 24 is negative 48. Let's put the x in the front and the rest of it. So we have x squared plus 12 to the negative 2 power. Now we can go ahead and find the second derivative in a similar way, except we will need the product rule as well as the chain rule this time, because we have this function times this function. So the product rule. We will take the derivative of the first function first. So the derivative of this yellow function is simply negative 48. And this first time through, we copy down the second function unchanged. So I'm just going to write x squared plus 12 to the negative 2 power. And then I do plus. Now I'm going to go through it again. The second time through, we leave the first function unchanged. So I'm just going to put negative 48x, and then we multiply by the derivative of the second function. So here comes the chain rule though, so I'm going to do negative 2 in the front. Okay, subtract 1, so that'll be negative 3. Write the inner function down, so I have x squared plus 12. And then I must multiply by the derivative of the inner function because of the chain rule. So I will I will multiply by 2x. So let's clean this up a little bit, and we have some factoring to do as well. So here's what I did so far. I multiplied negative 48 times negative 2 times 2, and that gave me the positive 192. Also, we had x times x, so I got x squared. I colored these factors in green to emphasize the fact that these are common factors. They both have the x squared plus 12. So let's factor this green stuff outside of the parentheses. Also, 48 goes into 192 4 times. So let's bring out a negative 48. So we'll have a GCF of negative 48. And then we're going to have this x squared plus 12 out in the front. We have to decide what power to bring out. Always go with the lower exponent. So negative 3 is less than negative 2, so I'm going to do negative 3. And then I have to decide what will be left inside the parentheses. Remember, when you factor something out, you divide to figure out what goes on the inside. So that's why negative 48 divided by negative 48 is 1, so we put nothing. But when it comes to the x squared plus 12, we're dividing x squared plus 12 to the negative 2 power is being divided by x squared plus 12 to the negative 3 power. So remember, when you divide like bases, for example, if I have n to the third power divided by n to the 12th power, you subtract the exponents. So this would be n to the negative 9 power. So that's what we're doing here, but I have to subtract negative 2 minus negative 3. But do you hear the double negative that I'm saying? When we do minus and negative, we add. So you're going to end up adding 3 to these exponents when you divide. So that's why we will have x squared plus 12, well, to the 1 power. So because it's the 1 power, I don't even really need these parentheses, do I? So let's just write x squared plus 12. All right, moving on to the next term. 192 divided by negative 48 is negative 4. But then don't forget about the x squared. That's going to still be there. For the x squared plus 12, this is gone because we have the 0 power. That makes this a 1. Or you could just say, well, we took this entire thing away when we brought it out to the front. Either way, that's it. So we can combine like terms here. So we're going to have x squared minus 4x squared. So this will be negative 3x squared plus 12. Let me bring this up to the next line. So now we have this. I'm noticing that in the second set of parentheses, there's a common factor of 3. So let's factor out a negative 3. So we will have f double prime of x is equal to negative 48 times x squared plus 12 to the negative 3 power. But now I'm going to take this negative 3 out. So that will leave x squared minus 4 on the inside. 48 times 3 is 144, so let's go ahead and put that down. I'm going to drop the x squared plus 12 to the negative 3 power down to the denominator because of the negative exponent. So we will have x squared plus 12 to the 3rd power down below. And we're left with x squared minus 4 in the numerator, but I think I'll go ahead and factor this now. So this will be x plus 2 times x minus 2. It's time to find those special numbers for f double prime, the values of x that either cause f double prime to equal 0 or the values that cause f double prime to be undefined, because those are the values that we need on the number line to make the sign chart. F double prime will equal 0 when the numerator equals 0. In factored form, we can easily tell that will happen when x is equal to negative 2 from this first factor, or when x is equal to positive 2 from the second factor. How about where f double prime is undefined? That will happen when the denominator is equal to 0. So that would mean x squared plus 12 would have to equal 0. However, if you subtract 12 from both sides, we get x squared is equal to negative 12. You cannot square something and get a negative number. So there are no solutions here. That means we have 2 special numbers to put on our number line. So here are the 2 special numbers in order on the number line. We have 3 factors to consider, so I'm going to put 3 rows on this sign chart. Make sure you label your sign chart as f double prime. We must determine whether these factors are positive or negative in each interval. X plus 2, if you set this equal to 0, you get negative 2, so that's sort of the cutoff. This expression will be negative for values that are less than negative 2 and positive for values that are greater than negative 2. So for example, if you picked negative 3, that would be negative 3 plus 2. That would give you a negative 1. If you picked a value greater than negative 2, like 0, then you'd have 0 plus 2, that would be positive 2. So that's how that works. Similarly, if you set x minus 2 equal to 0, you get 2. So that's the cutoff for this factor. So you will get a negative result for x values less than 2, and you will get a positive result for x values that are greater than 2. What about x squared plus 12 to the third power? This will always be positive because no matter what you put in for x, when you square it, you're going to get a positive number. Add 12 to it, still positive. Cube it, still positive. So what about the overall value of f double prime? Just focus on the negatives. If we have an even number of negatives, that's going to give us a positive overall value for f double prime. We have a single negative factor for the middle column, so the overall value of f double prime will be negative. In the third column, it's all positive, so f double prime will be positive. Remember the relationships. If f double prime is positive, f is concave up. If f double prime is negative, f is concave down. That means the original function should be concave up in this interval from negative infinity to negative 2, and it should be concave up in this interval from 2 to infinity. It should be concave down in this interval from negative 2 to positive 2. So we just need to write all of that up. We say f of x is concave up from negative infinity to negative 2 and from 2 to infinity because f double prime is positive. F of x is concave down from negative 2 to positive 2 because f double prime is negative. According to the directions, we must also comment on the points of inflection. So notice that f double prime goes from positive to negative at an x value of negative 2. So that's a point of inflection. And f double prime goes from negative to positive at x equals 2. So that's another point of inflection. Let's add that into our final answer. F of x has a point of inflection at x equals negative 2 and x equals positive 2 because f double prime changes signs. Let's start out by finding the first derivative on number 15. So let's see, 3x squared minus 12x plus 12. That's the first derivative. Let's go straight into the second derivative. This will be 6x minus 12. Let's write this in factored form to make it easier to find those special numbers. So we have 6 times x minus 2. We need to know the values that will cause f double prime to either equal 0 or be undefined. This is a polynomial, so there are no values of x that will cause this to be undefined. But where will it equal 0? Looking at this factored form, we can just immediately tell it will equal 0 at x equals 2. So that is the one special number that we need on the sign chart. So let's put that on the number line. So here's your x equals 2 on the sign chart. There's only one factor to consider. A positive constant doesn't really change anything. So we only need one row. Make sure you label your sign chart as f double prime. So let's consider whether x minus 2 is positive or negative in each interval. If you pick a value of x that is less than 2, like 0, if I put in 0, I would get negative 2. So it's negative in this interval. If I pick a value of x that's greater than 2, it will be positive. We have learned that if f double prime is negative, the original function is concave down. So it should be concave down from negative infinity to 2. If f double prime is positive, the original function is concave up. So f should be concave up from 2 to infinity. Let's go ahead and write that down. So f of x is concave up from 2 to infinity because f double prime is positive. F of x is concave down from negative infinity to 2 because f double prime is negative. We also need to mention the points of inflection. So because f double prime goes from negative to positive at an x value of 2, we can say that we have a point of inflection at x equals 2. However, this time they want us to be more specific than that. They said find the points of inflection. So we need to actually find the x and the y value instead of just the x value. So we know that there will be a point of inflection at x equals 2. How do we find the y value? We simply substitute x back into the original equation and see what we get. If you plug 2 in for all the x's, you get y equals 8. So there's a point of inflection at 2, 8. Let's add that to our final answer. F of x has a point of inflection at 2, 8 because f double prime changes signs. Let's do one more, shall we? This one is going to require the product rule. We will look at this as this function times this function. So f prime equals, we take the derivative of the first factor, which is 1, and then we multiply by the second factor left unchanged. This is the product rule. We put a plus. Then we go through it again. The second time we leave the first factor unchanged and we multiply by the derivative of the second factor. So the derivative of the blue part, see there's the derivative of the outer function, and you leave the inner function the same. Then you multiply by the derivative of the inner part, but that's just 1. So I don't really need the 1's on the ends of these. Notice that we have this factor of x minus 4 in common with both terms. Let's factor that out and put the x minus 4 in front of parentheses. But what exponent should we use? Always go with the lower exponent. So I see the 2 here, so I'm going to factor out x minus 4 to the second power. When you factor something out, you're really dividing. And when you divide like bases, you subtract exponents. So I'm going to do 3 minus 2. So this is going to leave x minus 4 on the inside because it'll just be the 1 power. Of course, I've taken the entire x minus 4 squared and put it out front. So there's nothing left except for this x times 3, which of course I'm going to write as 3x. So I will have plus 3x on the end of there. Let's go ahead and combine like terms. The x plus 3x will make 4x. So I have 4x minus 4. Let's take out the GCF of 4. I took that GCF of 4 and put it all the way in the front, but that left behind x minus 1. This is f prime. It's time to go ahead and find the second derivative, f double prime. So I'm going to take the derivative of this. Let's use the product rule. I will look at f prime as this yellow function times this blue function. So, product rule. I'm going to take the derivative of this first part, the yellow part, and leave the blue part unchanged. So I'm going to do the chain rule on the yellow part. Taking the derivative of the outer function, it'll be 2 times 4, so that'll be 8. So I have 8 times x minus 4. So that's the derivative of the outer function. Normally I would now multiply by the derivative of the inner function, but that's just a 1. So I don't need that. And I can leave the second part the way it is. And then I put a plus. And you go through it again. The second time through, you leave the first part alone. So I'm just going to copy down the 4 times the x minus 4 squared. And then you multiply by the derivative of the second part. But the derivative of x minus 1 is just 1, and I don't really need to write that down. So that's it. This is the second derivative. I am going to factor some things out. So notice that we have a common factor of x minus 4. Maybe I'll just get this started right now. So I'm going to take out an x minus 4. And I see, looking at the 8 and the 4, there's a common factor of 4. So I'm going to pull all that outside of parentheses. If I take out a 4, so this 8 is going to become a 2. I've taken out the entire x minus 4 from this first factor, so that's gone. It is going to leave behind the x minus 1. So I'm going to have this 2 times x minus 1 sitting there. Now I've taken out a factor of x minus 4, but from this second term I have x minus 4 squared. So I'm basically going to subtract 1 from this exponent, or I'm taking one of these factors away, which leaves 1 behind. I took out the 4 as well, so this 4 is gone. So all that's left is the x minus 4, one of the x minus 4s. So I have this. This can be simplified. I think I'm going to bring it up over here. I distributed the 2 and I got this. Now let's just combine like terms here. So I've got f double prime of x is equal to 4 times x minus 4 times, 2x plus x is 3x, negative 2 and a negative 4 make negative 6. There is another GCF in here. I'm going to take out the 3, but that 3 is going to wind up multiplying by the 4 to make a 12. So f double prime of x will equal 12 times x minus 4. So I've divided by 3 now, so this will be x minus 2. Okay, time for the special numbers that make f double prime equal to 0. If this weren't a polynomial, I would also look for values that would cause f double prime to be undefined. But there are no values that could possibly make this undefined. The values that will make this equal to 0 are x equals 4 because of this factor, and x equals 2 because of that factor. Let's put these special numbers on a number line and make a sign chart. So here are my 2 special numbers on the number line. I have 2 factors to keep track of, so I will need 2 rows. I don't need a row for this 12 because it is a positive constant which will not affect the signs of anything. Make sure you label your sign chart as f double prime. Now let's determine whether each of these factors is positive or negative in each interval. X minus 4. If you set this equal to 0, you get x equals 4. So 4 is the cutoff. If you choose a value of x that is less than 4, then the expression will be negative. For example, if x is 0, then you just have negative 4. If you choose values of x that are greater than 4, x minus 4 will be positive. For x minus 2, you set that equal to 0, you get 2. So 2 is the cutoff. If you pick a value of x that is less than 2, you're going to get a negative result for the expression. For example, again, if x is 0, that just leaves negative 2. If you pick a value of x that is greater than 2, then x minus 2 will be positive. For example, if you pick 3, then that's 3 minus 2, positive 1. let's think about the overall result for f double prime. We would have a negative times a negative in the first column, so that would be a positive. A negative times a positive is a negative, and a positive times a positive is a positive. We learned a long time ago that if f double prime is positive, f is concave up. If f double prime is negative, f is concave down. That means the original function should be concave up in this interval from negative infinity to 2, and it should be concave up in this interval from 4 to infinity. F should be concave down in this interval from 2 to 4. Let's just write that up. So far we have this. F of x is concave up from negative infinity to 2 and 4 to infinity because f double prime is positive. F of x is concave down from 2 to 4 because f double prime is negative. We still have to discuss the points of inflection. So notice that f double prime goes from positive to negative at x equals 2. So there is a point of inflection there. It goes from negative to positive at x equals 4. So that's another point of inflection. We need to find the y values as well though. So I'm just going to use this as scratch paper. So at the moment, we know that x equals 2 and x equals 4 are the two x values of our points of inflection. To get the y value, we need to go back to our original function. So we have x times x minus 4 cubed. So y equals 2 times 2 minus 4 cubed. And y equals 4 times 4 minus 4 cubed. 2 minus 4 is negative 2. Negative 2 cubed is negative 8. Negative 8 times 2 is negative 16. And 4 minus 4 is 0, so this just gives us y equals 0. So that means we have a point of inflection at 2 comma negative 16. And we have another point of inflection at 4 comma 0. But let's write this up properly. So f of x has a point of inflection at 2 comma negative 16 and 4 comma 0 because f double prime changes signs.